Hello, my dear students, and welcome back to the third part of our case study considering the lighting loads in an office building in Nairobi, in Kenya. In the previous two parts, we were more oriented to the load optimization, the energy management, the energy auditing, the different levels of energy management and energy auditing, the motion detection sensors, and its effect or its impact on the overall energy saving. Today, and in this third part, we are going to focus toward the PV part, especially the first case where we are considering the PV on-grid systems. So let me start sharing my screen and let me go directly to remind you with what we did in the previous part. So in the previous part, we have, yes, here, this is the Excel sheet. Here in the previous part, we have concluded this amount of energy as the total energy needed per day for the lighting loads in the office building, considering these lighting loads as demonstrated in the example. Now we are going to proceed with, as I mentioned, the PV part. So I'm going to create a new sheet here where I'm going to start the PV on-grid sizing steps. So let's start these steps together. Okay, let's do it. First, we have a total energy of about 35.79 kilowatt hour per day. This is after applying the motion detection sensor, as you can find it here. So this will be our main input for the system. What I'm going to do now is that simply I'm going to Control C, and then I'm going to paste this. Of course, here we have an error because we have to take this number separately, copy, and paste it here as, or it's better not to paste it as it's better to make it like this, equal, and let's make it like this. So we can have a dynamic numbers across sheets. Okay, so this is the beginning, or this is the first part of the story, as you can see. Okay, so let's start considering these calculations together. Now we need to start making the rough estimation for the PV sizing process. And as you know, we start to make some sort of equalization between what we supply and what we consume. This number, which is a 35.79, represents the consumed energy per day in the building, considering the lighting loads. But let's go to the other side of the story, and let's consider together what we are going to supply. If we return back to the question, you will find in the question that I input you with here, I think somewhere. Yes, I'm input you with this the sun module SW with 260 mono. This is 260 watt PV module with about a price of $225 per module. Of course, this will be considered in the next phase, which is the economic part. But now for the technical part, let's consider the data sheet. If you go to the data sheet here, this is a data sheet attached. So as you can see, this is a 260 watt module. You will find this typically in the second page, I think. So yeah, this is a 260 watt peak module. And if you go back to the question, you will find that considering the irradiance, we have mentioned somewhere here. Yeah, this is the area. We will going to use it somewhere in the next step also. And also, I think we have the radiance given. Yes, this is the typical average radiance, which is 4,067 watt per meter squared per day on average. So using this number, we can calculate the estimated, what we can call the peak sun hours or the equivalent sun hours. Simply, you know that one sun represents 1000 watt per meter square. So whenever you have 4067 watt per meter square, that represents roughly 4 hours of peak sun hours. So here, our peak sun hours, course unit here is hour, will be 4 peak sun hours, just for a cosmetic reason. Let me go now here to the borders, and let's make a normal borders everywhere. Okay, so this is the peak sun hours. And considering that we have our PV model, PV watted per module, here I will make the unit kilowatt just to unify kilowatt everywhere, because here, as you can see, the energy is given in what the energy is given in kilowatt hour. So to make everything in kilowatt, it's better to make it here in kilowatt, and then this 260 watt will be turned to 0.26 watt, as you can see in this example. So using these two numbers, I mean the wattage per module and the power given for the wattage per module and the peak sun hours in hours, using these two numbers, you can now calculate what we can call the expected energy to be produced per PV module. So energy generated per PV module per day. This energy generated per PV module per day will be simply the multiplication of these two numbers. So this 4 hours times 0.26. So this will give about 1.04 kilowatt hour per day. This represents the energy to be generated by a single PV module. So if a single PV module, we're going to generate a 1 kilowatt hour per day, and you require 35.79 kilowatt hours per day as a supply or as a load, you can simply calculate here the number of modules here. You can calculate it simply as the division between this number and this number. This will be, as you can see, which is around 34.42, and we can round it up to be 35. So this is the system you require, but one of you will stop me for a while and you will tell me that this is not correct. This is what you can call somehow an ideal model. Why this is an ideal model? Because simply when I do this calculation, I ignore any sort of losses that might happen in the system. And by force, we have a lot of sources for losses, including but not limited to the cable losses, or the voltage drop across cables, the losses in the DC-DC converters, is the DC-AC inverters, even in different types of connections, and all these types are considered as losses. So you can go to here in order to calculate the losses. I think somehow given one by one, maybe you can find it. Or what I can simply do is that I'm going to make some sort of a general losses term. So let me assume overall on grid losses of 0.2, which means 20%. Okay, so simply what I can now calculate is what I need to generate in exact is not this number. What I need to generate is not this 35.79 at the power. What I need to generate is simply power energy to be generated considering losses. This number can be this number over 1 minus 0.2. So as you can see, I'm sorry, I think I did a mistake here. So this number over 1 minus 0.2. So I need to generate 44.75, something like that. This is simply what I need to generate. It's again much greater than this number because I'm now considering losses of a 20%. Okay, so this is what I need to generate across the system. So now I can recalculate the number of PV needed in the ideal case. So what I can see, or what I can do now is, again, we can write now this number of PV modules, not ideal, this is the real number. So this, in this case, this will be this 44 divided by this 1.04, which is 43.025. And again, I will round it up to 44. Again here. Sorry. And again, this will be the needed number of PV modules. So we need 44 PV module in order to implement our system. Our system, we're going to generate 44.746 kilowatt hours per day. Again, I here need to kilowatt hour per day. This system, we're going to generate 44.746 kilowatt hour per day. And when I consider this system at 20% losses, the load will be reached by 35.76968 kilowatt hour per day. Okay, so this is the amount of energy generated. Let's calculate now the wattage of the system. We can calculate now the system wattage. Here we can calculate it very simple because we are using 44 modules. Each will be of 0.26 kilowatts. So simply our system is 11.44 kilowatt system, PV system. So I'm sorry, this is kilowatt. Again, so this is the PV system in calculations. And now I think everything will be ready to start our calculations. Of course, maybe we can make one final check in this sheet, so we can calculate or we can estimate the area. So this estimated area, if you remember, we estimate that every kilowatt PV system will occupy about 10 meters square. So this will end up that we need about 114.4 meters square. And if you return back to the question, you will find that you have an available area of 1,000 meters square, which is much greater than what you need. So in our case, the area is not a restriction in implementing the system. So this is simply the case where we implement our PV system and where we calculate the needed amount. So I think this concludes the first initial part of the sizing, where you calculate the number of PV modules, you calculate the number of the total wattage of the system, the area needed, let's say the macroscopic number that you need in order to implement your system. So this is simply a very valid example where you can do your initial calculations in this direction. Now we have two directions to proceed in. The first is to proceed with the other system, the other blocks in the system. I mean, to go to the DC-DC converter, to go to the DC-AC inverter, to proceed more and more. And also we need to go with the cash flow and the energy yield per year across the different years of the system and so on. So this is simply how we can proceed with both in both directions. Let me first go with the proceeding with the system. I think it's very straightforward in our case that we have single phase loads, as you can see here. I think, yes, you will find it here. Yeah, this is a single phase lighting load. So simply what you are going to make is that you are going to make a linking with a PV system with a single phase inverter. What you need to determine is the wattage of your inverter. So you have 11.44 kilowatts. So maybe you can search for 20 kilowatt, 25 kilowatt inverter. And using this inverter, you can check the conditions of the rating power of the inverter and so on. So let's do this task together now. So now I pick up an example for this is a 20 kilowatts, I think. Yes, so this is a 20 kilowatts PV or a DC-AC inverter. Now, what is really critical whenever you check the data sheet, let's assume that this data sheet is given for you in the exam. What is really critical when you check the data sheet of this inverter is that this rated input voltage. So here the inverter is expecting 620 voltage DC in the input terminal. And if you go to the data sheet of your PV, so this is the data sheet of your PV, you will find that the maximum power point voltage in your case is 30.7. So what is really important now to do is to do the following. What you are going to do is VMP per module. Of course, here the unit is volt. This is 30.7. I'm sorry again. And inverter rated input voltage, of course, in volt. So this is 620. So now what we are searching is when we divide these two numbers together, that calculates the number of PV modules you need to connect in series per string in order to fulfill this voltage. So simply when I divide this 620 over this 30.7, which ends up with about 20 point something, this number represents the number of PV modules per string. Typically, in our case, we have a 44 module, so we cannot make a 2020. Then we will have our remaining 4. So what makes sense here is to upgrade this into 22. So now you have 22 module connected in series per string, and that's typically mean that your number of strings will be simply this number divided by this number, which is simply 2. So now you can answer the question related to the topology of the system, or how you are going to connect the system. So you are going to connect the system in terms of 2 strings, each string of a 22 PV module connected in series in order to fulfill this inverter requirement. So this is another example or another input you need. So now you know the input. Typically the output will be either 3-phase or single phase, so you don't need to think about the output. This will be directly connected to the net metering and then to the grid and so on. So this is simply the givens or the requirements you need to. So I think you calculate everything now related to this, and this we can call PV tech site. Okay, so I think that conclude the numbers we need in this direction. Now we need to go to the second or the third sheet related to how we can manage the economic part, PV part. Let's do it side again. Okay, so now we have the economic port. Okay, how we can manage the economic port? First of all, we have to go to the lifetime expected by the system here. I think we already have this number given somewhere. So I think it's 20 years, but let me check it again. I think it was 20 years. Maybe somewhere in the beginning. So this is about the lifetime. Yes, okay. Yeah, maybe in the economic port here. Yeah, this is the inverter. We given the cost of the inverter. Yes, yeah, this is, yeah, typically, yeah, this is 20 years. So let's assume that this is a 20-year system. So let's start now working with that. So now, considering the year, we have starting from year number 0. We can roll down to get our 20 years. Okay, so these are our 20 years of operation. Before going into the economic part, the money, the cost, let's first consider more toward the energy yield part. So starting from year number 1, the system should start to generate energy. So this is generated energy. So with respect to our calculations that the system is going to generate, the system is going to generate this 44 kilowatt hour per day. However, we expect some sort of a 20% losses in the system. So what will reach typically the load or the grid will be this 35 point something kilowatt hour per day. Assuming that this was calculated based on an average equivalent sun hours or average peak sun hours, so we can say that the total energy yield starting from year number 1 will be this number, will be this number multiplied by 365. So this will be, I think I did a mistake here. So again, it is this number times 365. Yeah, so this is correct now. So this will be typically the energy yield per year. And here it's better in order to make life more easy and to turn it to be megawatt hour per year. So in order to make it in megawatt hour per year, I'm still missing to divide by 1000 here. So that means that you are going to generate about 11, or not 11, I'm sorry, 13 megawatt per year. This is the expected energy to be generated per year. Here we have to consider a factor that by generating this 13 megawatt hour per year, this production or this energy generation will be affected during the lifetime of the system by an incremental decrease or some sort of a yearly decrease, an annual decrease in the energy generation, because simply we know that during the lifetime of the system, which is typically from 20 to 25 years, the system performance is degraded by around 20% of its rated output. So that means that in 20 years, we are going to make some sort of reduction in the power. So in year number 1, for example, number 2, for example, what we are going to get is we are going to get this energy times 0.99, for example. So we are going to lose roughly 1% per year. This is not an accurate way to do it, but it's roughly good way to make it in some sort of a compromisation between accuracy and simplicity. So you can now calculate this to estimate the energy production across the year, and you can see that during the 20 years of operation, your system will going to lose around 3 mega of its yield. Here, this is a very important and a very critical point in your design, because when you design your system for the first impression, you manage to make an output which is typically equal to your expected load. Now, from the load perspective, your load should roughly be the same in the next 20 years. So in here, I consider load megawatt hour per year. Here, as you can see it, this will be simply this number. But the point is, this number will not decrease. The load will not decrease. I'm sorry, I make it wrong. So what I can do here is that I can dollar sign here. So this is a dollar sign and then another dollar sign. And then we can roll it down like this. So the load is roughly constant among the lifetime of the system. However, your energy production or your energy generation is decreasing with this 1% or whatever. That's mean that by going into more and more years in the life cycle or the lifetime of the system, your load is going to, or sorry, your system is going to supply less energy than required. So simply we can make it if we did something like that. So here you can see it, my dear students. The one in orange represents the energy by the load, expected by the load. And the one in blue represents the energy need to be or expected to be generated. And as you can see, going to the 20 years of the system, there is a gap between these two rounds. And here you have to take a decision. Okay, what should be your decision? Simply, you have two decisions to be taken, or one of them, I mean, to be taken. Either to oversize the system. So you can say, okay, I need to go in a condition where the minimum voltage, the minimum power or the minimum energy, the minimum energy to be generated is equals to the load. So simply I'm going to shift this blue curve or this blue line upward so that the minimum come here. Then you are going to generate more energy than you need, but that will impact the total levelized cost of energy because simply you are oversizing the system. The second alternative is to accept the condition and to use your grid in order to access the gap between these two rows, these two columns. I mean the supplier and the demand. So you can never say which one of these two conditions is better. You have to make a try in both directions in order to determine the levelized cost of energy in both cases. And then you can make a conclusion. And again, if in this case, we reach a conclusion that, for example, taking the energy from the grid is much better in an economic way, this decision cannot be propagated to other case studies. Because as you know, simply, my dear student, there are a lot of factors that affect this decision. For example, the tariff, the electricity tariff changes from one country to another. The peaks and hours change from one country to another. A lot of parameters that change in the system. So it can never be a standard decision. This should be a case-by-case decision based on your case, based on your story, based on your case study. So just to make our video short, what I'm going to do is that I'm going to make one of these two solutions. And I invite you, my dear students, to do the other case and return back to me and tell me what is your conclusion, which will be better. So now what I'm going to do is that I'm going to go to the second scenario where I'm going to assume that the energy required or the extra energy needed will be supplied by the grid. So what I'm simply do is that I'm going to say that, okay, energy needed from the grid still in megawatt hour per not day, it's per year. So simply it will be subtraction this and let's subtract this from this. So here. I think I did something wrong. Yes, I know I did something wrong. So yes. And then here you can calculate the energy needed to be taken from the grid across the system. So this is simply the case study you are going to. So this is an initial way in order to start the economic part of your study. And before going more and more here, so let me make it in a more cosmetic way. So let's do this in a better. Okay, so now from these numbers, we need one sum, which is the total energy to be generated by the system. This is a very important number for us. Why? Because when we start to determine the levelized cost of energy, which is the key indicator in this study, what we are going to do is we are going to divide the total energy the total cost of the system over the total energy generated by the system. So the total cost of the system here, the total energy generated in 20 years, keeping the unit is megawatt hour per day. I'm sorry, not per day, it's per year. I'm very sorry. And this simply will be the sum of this data. So this 237.9 megawatt hour is the total energy to be generated by this system. Okay. Okay, so this is simply how life is going with respect to the system. But let's now go to another side of the story, which is the economic part. Here we have different sources of money to be consumed, starting with the capex or the capital cost. Usually, we can divide the capital cost of the system into three big portions. The first portion is the cost needed for a PV modules itself. The second portion is the cost needed for the DC AC inverter. And the third portion is the other accessories, legal documents needed to be purchased or needed to be issued, connection, net metering fees, all other stuff. So let's now start to calculate the capex with respect to these three big numbers, I mean. So let's go with the first one. So now I'm going to calculate three numbers. Let me calculate them here, and then we sum them in the end of the system. So first, let's go with the cost for the PV. So I'm going to calculate three numbers here. First is first is the PV cost. So the PV module cost is very simple. I think we already have a given here related to the cost per module. I think I already saw, yeah, it's $225 per module, and already we know the number of modules we need. So simply the total cost of a PV will be $225 times the number of PV modules, which is 44. So simply this results the cost for a PV module. And the cost for the inverter, again, I think we have a guide for that. So if you go here, you will find that I told you that per 1 kilowatt, let's assume a cost of $100. So your system, or in our case, we used a 220 kilowatt PV DC-AC inverter. So we have $100 times 20, which is the kilowatt of the PV. I think I'm writing in the wrong place, so I have to stop here. So this is $100 times 20. Of course, these are some sort of an estimated number. So this is DC AC inverter cost. And again, in terms of the other costs here, the other direct and indirect cost, I think assuming here that with considering area, which is 9% from, yeah, it's 9% from the other capex. So other direct cost, here you can say that it's simply equals to 0.09 times open bracket this number plus this number, then close the bracket. So this will be the other cost, and then the total capex is simply a sum of these three numbers. Okay, so that this $12,971 represents the total cost of the system. Now we can start putting this here for the capital cost. And you can use here this. So the capital cost is in year number 0, which will be reflected from sheet number 2, this number. So this is the capital cost. Okay, great. So now we finalize the first source of cost, which is the capital cost. The second sort of a cost is the operation and maintenance cost. The operation and maintenance cost, I don't know if there is something about it here or not. Yes, he enforcing us to use a 5% of the capex as an operation of maintenance cost. Of course, he is paid a year. So considering this in year number 1, yes, this is 0. Okay, so this is 1. So in year number 1, we are going to have this 5% from this capex. And then we are going to use a sort of inflation rate. I think we have an 2.7 inflation. So starting from year number 1, we are going to apply the equation, which is the present cost times 1 plus I, which is 0.00 not 1.027 to the power n. So this is the effect. Yes, I think it's now going in the right way. So I just need to copy the format here. Yeah, I just checked that this is an increasing number, so I think the function is correct. And then we can roll it down, but just we need $2 the present cost. This is what we need to do. And then we can roll it down. So this is the total cost need to be paid across the lifetime of the system. So now we did the operation and maintenance cost. Okay, now we have another source of cost, which is the replacement cost. And for the replacement cost, it's only once because our system is 11, is 20. We have to go to the year number 11, this one. Sorry, yeah. So this one, and then we can go here, and then we can calculate it, which is the present cost from the inverter. I think we already have it here, which is this is the DC AC inverter cost of this number times, open the bracket, 1 plus 0.027 to the power, and let's go. I'm sorry. Here we have to put the power sign, and let's go to the number 11, and then plus. So I think I have an error here. So let's make it again. It's a bit complicated equation because I'm capturing data from different sheets. So let's do it one more time. So this is the DC-AC inverter cost, yes, times 1 plus 0.027. Let's close the brackets, make the power sign, and go to number 11. Yes, and then press OK. Yeah, so I think there is something wrong with that. Maybe in the first number. Okay. So let me try to repeat it one more time. Well, yeah, I got the mistake. So this is not equal. This is plus. I'm sorry for that. I think it's now correct. Yes. So this is the cost in year number 11 related to the replacement cost of the inverter. And this is very nice indeed. So, okay, so we did it down for the replacement cost. So we have the capital cost, the operation and maintenance cost, the replacement cost. Sometimes whenever we have a salvage value for the system, we can insert it as a salvage value for the system. If we think that this is important, I don't think that this is given here. I don't think so. I couldn't find it. Maybe you can put it or not as you like. Of course, as I'm always mentioned to you, this is an open question. Considering the exam, this is an open question. So you simply can assume it and put your assumption. So we don't need to have a model answer for this. So just feel free to do whatever you feel it's appropriate for your question. But here we have a fourth item of cost, which is a very important cost. I mean, here we have the fourth item, which is grid cost. If you remember, my dear students, I already mentioned that I'm going to the route where I'm going to produce less energy than I need, and I'm going to access the grid to get this extra needed energy. So as you can see here, my dear student, that in our case, this is generated, this is the load, and this is the energy to be captured from the grid. And following the question we have, I think, if we go up here, yes. Yeah, we have this number. So the grid now in 2024 costs as an electrical tariff of 0.16 kilowatt hour, $0.16 per kilowatt hour. So simply what you are going to pay is the energy you are going to supply it from the grid, energy you are going to take from the grid, multiplied by this 0.016. But don't forget two main factors, that here we are considering megawatts, so you have to multiply this 0.16 times 1,000 to be a cost for 1 mega. And another important point, which is that you have to consider the inflation rate again for the tariff. So what you are going to do here, start calculating the tariff, and let's start with this 0.16 times 1,000. So this $160 per megawatt. So we can write it here that this is dollar per megawatt hour, just not to forget. And now we can apply the tariff, the inflation rate equation. So this number times 1 plus 0.027 to the power, and let's here go it like that. Okay, and then we have to $sign the first present value. And we can also use here this cosmetic issue to make all cells appears with the same style. Okay, so this is simply the cost in year number 2, and then so cost to be paid to grid is simply the multiplication between this number, energy needed from the grid, times this number, course starting with 0. So let's do it like that. Okay, so this is how much money you are going to pay per year across the lifetime of the system. Now we have calculated all the portions of the total cost. So the total cost of the system is simply, we can start from here to make sum. And let's make it like that. And now let's use a yellow color. This is an important numbers. Of course, we don't need this number. So this is the 4 portions. This is the capital cost, operation and maintenance cost, replacement cost, and the cost for the money, or the cost for the electricity coming from the grid. These are the 4 portions where we have the grid. So maybe we can make it like that and like that. And we can go to insert, and let's do it in the form of a pie chart, for example. So as you can see, my dear student, this is charted very nice to tell you what did you pay or what are you going to pay this. So the cost from the grid is maybe less than the quarter. Maybe most of the cost are the operation and the maintenance cost, because here we are using a relatively high value, 5%. And of course, the capital cost is dominating cost. So these are the dominating costs. This, of course, depends from one country to another again. Maybe in other countries, we have an operation and maintenance cost of 1% only. So this will affect the system cost. But again, this is just example to learn, nothing beyond. So this is the energy generated. Again, I will do it in yellow. So let's now calculate system cost. This is an overall system cost. So this is simply, let me merge all that. And let me say that, okay, this is equal this one plus this one plus this one plus this one should be in yellow. So this is a overall system cost, which is about $38,456 among 20 years. And this is the energy. So now you can calculate the LCOE. Simply, the LCOE is cost per kilowatt. So what we're going to do is to divide this over this. So as you can see here, this is around 160 watt. But again, don't forget that the unit here is megawatt hour per megawatt hour or dollar per megawatt hour, because this is in megawatt. So in order to make it in kilowatt, so if we need to make it dollar per kilowatt hour, so you have to make another, you have to open a bracket here and then divide by 1,000. And you can find that this is typically 0.16, which is something amazing. Why it's amazing, my dear students? Because simply, this is typically what the guy in Nairobi is paying now in 2024. So you're telling him that by doing this system, you are going to maintain the electricity cost constant for 20 years. So whenever there is an inflation or whatever economic conditions happen, your system will not be affected in a big portion, because most of your cost is in the capital cost, which will be paid in 2024. That's will immune you from any economic changes in the prices of electricity and something like that. So you fix the electricity cost in 20 years. And this is something very, very beneficial for a system. And I think this concludes what we target for this part, which is the AC, sorry, not the AC, the PV on-grid system. Maybe later on, I will try to do another video for you to consider what if we are still in Nairobi, but we are in a place off-grid. We don't have a grid, so we have to go with an off-grid solution with batteries, with diesel, how we are going to solve this. So this will be a part of maybe a next video. Thank you very much for your concentration. And I hope that this video adds something for you. See you later on. Bye-bye.